Okay, so thank you. So thank you very much for the invitation. And yes, as you may have seen, I will be giving a bunch of talks about different aspects of the Cuntz group. So if you will, you can take this as a mini course on this invariant. So mainly the way that I've decided to organize this is that in the first talk, I'm going to be giving an introduction to the Cuntz group, as the name suggests. And basically, I will be giving let's say, the first definitions and the first results that one needs for all the other talks. And then the other 3 talks will be 3 research talks about 3 different open problems that have to do with the Cuntz group. And in those talks, I will also be giving some small introductions to more advanced techniques and more recent results. Okay, so that's the way that this is going to be organized. Okay, so let me start at the very beginning, which is with the definition of what the Cuntz group is. And to do that, I think that it's always very useful to recall what the Murray von Neumann semigroup is, which I'm sure that everyone here is familiar with. But still, it's useful to have it written down explicitly, because then the Cuntz group will just be a generalization of this. So, definition, the Murray von Neumann semigroup. And well, as all of you know, this begins by taking 2 projections, P and Q, in a C-star algebra A. A and B will always be C-star algebras in all of my talks. And then one writes that P is Murray von Neumann superequivalent to Q, if only if, by definition, P is P star and P star B is less than Q. So Q acts as a unit on B star B for some P in A. And you can also define an equivalence relation by saying that P is equivalent to Q if P is B star and B star B is equal to Q. Right? So again, as all of you know, this is an equivalence relation, and so you can perform quotients with it. And so you define the Murray von Neumann semigroup to be the quotient of all the projections in the stabilization of A modeled by this equivalence relation, where, of course, here you can just take all finite matrices over A, but I have a vested interest in writing it this way. And so, well, this is not the Murray von Neumann semigroup, this is just a set, and the semigroup is this set with the addition induced by diagonal addition. So one sets this and equips it with this addition. So P plus Q is just this thing here, right? So that's the Murray von Neumann semigroup, and by construction is a monoid. So it's a set with an addition and a 0 element, right? Which is simply the class of 0. And that's the difference between a semigroup and a monoid. A monoid must have an identity for the operation, and a semigroup can or cannot have it, right? So, well, it's called a semigroup for historical reasons, but it's actually a monoid. Now, under certain circumstances, you can make B of A into a positively ordered monoid. So you can equip it with an order. So namely, if your C-star algebra is stably finite, then the Murray von Neumann equivalence is nothing more than the symmetrization of the subequivalence. So P is equivalent to Q, if only if P is subequivalent to Q and Q is subequivalent to P. Almost by definition, if you will. So in particular, what this means is that B of A, or rather, this relation in B of A, P less than or equal to Q, if P is subequivalent to Q, where all this is happening in A tensor K, is a partial order on B of A, right? So this is a partial order on B of A, and in particular, B of A is a positively ordered monoid. What does this mean? Well, it's a positively ordered monoid is a monoid with a partial order in such a way that every element is positive, so every element is greater than 0, and in such a way also that the partial order and the addition work well with each other. Okay. So under this condition, you get a positively ordered monoid. As I said, I assume that everyone is familiar with this, but what I'm about to do is generalize this construction. Okay, so well, as all of you know, B of A is an extremely nice and extremely useful invariant. It's been used successfully many, many times, and not just in sister algebras. There is even a version for rings, which is now central in the study of algebras and rings. And so the idea behind the Cuntz semigroup is to say, well, let's take this definition and let's change every projection for a positive element. And the reason why you may want to do this, of course, changing what the superequivalence is. And the reason why you may want to do this is that there are many sister algebras that don't have that many projections. And there are even some that have no projections, and 0. And so the hope is that by changing projections for positive elements, you will get an invariant that will tell you something about those sister algebras. Right? Simply because there is always an abundance of positive elements in any sister algebra. So that's the underlying idea of the Cuntz semigroup. Okay, so definition. This is the original definition is due to Cuntz from 1978, but the version that I'm going to be giving it is the one by Eduard, Eduard, and Ivanescu, and this is from 2008. So there are two versions of the Cuntz semigroup. There is the classical one, which is this one, and then there is the modern one, which is this one. And nowadays, essentially, everyone uses this one. And during my talks, I will just use this one. Okay. So what's the Cuntz semigroup? Well, as in the Murray von Neumann case, we start by taking two elements and defining a superequivalence. So now the elements are not projections, but positive elements. And then we say that A is superequivalent to B, and this already appeared on Tuesday, and implicitly also last week in all of the talks. One says that A is Cuntz superequivalent to B if A is the limit on n of Bn, B, Bn star for some sequence Bnn in A. So that's the let's say the Murray von Neumann superequivalence version for positive elements, and it's known as the Cuntz superequivalence. And then mimicking what happens in the stably finite case, one says that A is equivalent to B if A is superequivalent to B and B is superequivalent to A. And now that we have this, we just copy the definition of the Murray von Neumann semigroup. So now one sets Cu of A, which is the Cuntz semigroup of A, we all the positive elements in the stabilization of A modded by this new equivalence relation. Where note that now it makes a difference to write A tensor K or just finite matrices over A. No. So this was just to say that P of A, you can make it into a positively ordered monoid in the stably finite case. And just to make the parallel that in the stably finite case, you could define the Murray von Neumann superequivalence by simply symmetrizing, which is what you do in general in the Cuntz semigroup. Okay. So, well, one sets this, and again, this is just the underlying set, and now you equip it with an addition and another, as before. So one sets this and equips it with the addition given by diagonal addition. This is slightly informal, but it's enough for this talk. And one says that a class of an element is less than or equal to another if in A tensor K, one is Cuntz subequivalent to the other. So that's the construction. That's the invariant in all of these talks. Okay. So now again we have a set with an order and an addition. So this makes it into a positively ordered monoid as well. So given any sister algebra, we have a way of constructing a positively ordered monoid, which is the Cuntz semigroup. So let me give you a couple of examples of Cuntz subequivalence. Remark. First of all, if you have two projections, this was also mentioned on Tuesday, then they are Murray von Neumann subequivalent, even only if they are Cuntz subequivalent. So this truly generalizes the Murray von Neumann subequivalence. And in particular, so, or equivalently, if you will, if A is stably finite, then B of A can be order embedded into C of A. So for general sister algebras, it follows from the construction that you can always map B of A injectively into C of A. You don't need stably finiteness for this. You simply take the class of a projection, take that projection, and take the Cuntz class, and that's the map. And that's injective always. But if you have this additional relation or this additional order in the stably finite case, then it's not just an injection, but it's an order embedding. Meaning that if you take the class of two projections and they compare in C of A, then they must also compare in B of A. Right? This is exactly what this is saying. Okay? So you can always recover B of A in some sense from C of A. Then just another example. If A is less than B in the order of the sister algebra, then A is subequivalent to B. And more generally, this also holds if A is in the hereditary subsystem algebra. Of this is a particular instance. I'm not claiming that these things are trivial. I mean, you have to prove things, but these are all true. Okay. So now, as I've said, one has a way of constructing a positively ordered monoid from any sister algebra, which is mainly this construction. And of course, you want to know what happens at the level of star homomorphisms. And it turns out that any star homomorphism descends to a positively ordered monoid morphism between Cuntz semigroups. And I will improve this result very quickly, but let me just state it. So given a star homomorphism, let's say phi from A to B, then the map C of phi goes from C of A to C of B. And well, as you can expect, this simply does this. So this is C of A. This is a morphism in the category of positively ordered monoids. Okay, so this is a positively ordered monoid morphism. Meaning that it preserves the zero element, addition, and the order. Right. So, okay, looking at this, you might say, well, for any sister algebra, we have a positively ordered monoid. And for any star homomorphism, we have a positively ordered monoid morphism. So the question is, should we think of the Cuntz semigroup as a functor that goes from the category of sister algebras to the category of positively ordered monoids? And the answer is no. because that functor does not preserve inductive limits. So what I'm going to do now is to introduce the right target category for Cuntz semigroups, which is known as the category CU of CU semigroups. And that category will make the functor continuous. That's the whole point of introducing that category. Okay. So this is section 1. Let's say the target category. So, as I said, you could think of the Cuntz group something that does this, but this will not preserve inductive limits. So this does not preserve inductive limits, which is a very desirable property when you want to compute things, right? Because usually most examples are constructed as inductive limits. So what I'm going to be doing is to introduce a subcategory of positively ordered monoids. This is called CU. It can get slightly confusing, but I'll just say that this is the functor and this is the category. And then when seen as a functor from C star to CU, this will preserve inductive limits. So the main point really, the reason why this functor from when seen as something that has target category P of monoids is not continuous is because you are forgetting the topology of your C star algebra. Essentially, this is what happened. This category is too big in some sense. So instead, what I want to do is to introduce a subcategory of positively ordered monoids that still have some sort of topological information. So that's where the compact containment relation comes in. And in a couple of minutes, I will give examples of everything. Okay, so this is just to introduce the notation. Okay, so the notation is taken from domain theory. And it's the following. So you take a poset and you assume that in this poset, every increasing sequence has a supremum. So let's take a poset such that every increasing sequence supreme. Then one says that some element X is compactly contained in Y, and it's written in this way, if whenever Y is bounded by some increasing sequence Zn, or rather by the supremum of this increasing sequence, or some increasing Zn, then X is actually bounded by one of the elements of the sequence. Okay, then X has to be bounded by Zm for some. So as an example, you could take P to be 0 infinity. So the non-negative extended real line. Then this is a poset where every increasing sequence has a supremum, because the increasing sequence is either bounded and the supremum is a real number, or it's unbounded and its supremum is infinity, which is already included. Right? So this is one such poset. And then in here you can prove that this is the same as strict inequality. So the compact containment relation is always a strengthening of being below one of the elements. So for example, I mean, the way to prove this, if you assume this and Y is a real number, you can take a strictly increasing sequence with supremum Y, then by definition, X will be strictly less than Y, because it will be less than one of those elements in increasing sequence. Okay, so that's how you prove these sort of things. Okay, so one is interested with positively ordered monoids that have this sort of structure, so that behave well with respect to this compact containment relation. So definition. This is our Eliot Manescu from 2008. One says that a positively ordered monoid S is a CU semigroup, which will be the objects in that category if four conditions are satisfied. And again, after this definition, I will be giving examples. So if the following conditions satisfied, the first condition simply says that we want to be in that setting. So every increasing sequence has a supremum. And so because we are in this setting, we can talk about compact containment relations. So the second condition is that every element is the supremum of a compactly contained increasing sequence. What does this mean? Well, it means that for any element X in S, there must be some sequence Zn such that Zn is compactly contained in Zn plus 1. For example, in that setting there, right, in 0 infinity, this is trivially true because the compact containment relation is just the strict inequality. So O2 is simply saying that every element here is the supremum of a strictly increasing sequence. Okay. So these are the two, let's say, topological conditions that you ask of your positively ordered monoids. And these two will make the functor be continuous. And then you also want to ask two compatibility conditions, but it's just so that everything works well with each other. So the compatibility conditions simply say that if you have two pairs of compactly contained elements, then the sum should also satisfy the relation. So this is y plus t. So it's just something that you ask to have some sort of compatibility, and the same with suprema. So if you have two increasing sequences, let's say xn and yn, since all elements are positive, this is also an increasing sequence. And so you ask this supremum to be this plus that. So this is a CU semigroup. Why do we care about them? Well, every Cuntz semigroup is a CU semigroup. That's the point. Yeah.
What you are saying is that this problem that you mentioned
What problem?
earlier, this category,
Yeah.
So by O1 and O2, so this problem is resolved.
Well, I still need to introduce who the morphisms are in this category, but essentially the point is that when you take just an algebraic limit, which is what's happening in the category of positively ordered monoids, you lose a notion of completeness, which is always in the category of sister algebra, something that's used, right? So an inductive limit in sister algebras, at the very end, you have to take a completion. And the issue is that if you take a limit in PO monoids, that completion is never taken. So that's why you need to add these sort of conditions. Okay.
Well, actually, my question is that in addition to O1, to
Yeah.
O4, also, I think the O2 has something like O3.
Yeah.
Right?
Yeah.
So
No, but that's something completely different. Well, it's not completely different, but I mean, it's not part of the definition of the category. So the objects are just given by these four conditions.
It's not true that every such, like, it's not known whether or not every.
No, it is known. I will now give an example.
No,
So-
no, I mean, it's not, I'm saying that the inverse. Like, is it true that every such,
No.
positively ordered monoid satisfying O1 through O4 is a Cuntz semigroup of
Yes,
Cuntz group?
that's
That is not-
that's known to be false, and I will now give an example.
But, sir, the other stuff, that is.
No, that's also known to be false. We have examples, so we are still missing things. Yeah. No, that's right. So, well, okay, the theorem, as I was saying, is again, so it's the same people. So CU of A, the Cuntz semigroup of any system algebra is a CU semigroup. And now I can give examples. So examples. If you look at the complex numbers, then these can be identified with n union infinity. So we don't get that much compared with the Murray von Neumann semigroup. So the Murray von Neumann semigroup of this is, as you know, the natural numbers, right? Simply, you have infinity here. Well, if you will, because we need every increasing sequence to have a supremo, but that's not the real reason. I mean, the identification is just given by the rank. So you take any positive element in A tensor K, you look at its rank, and that's the element that you send it to. And that's an isomorphism. Okay. So this is a first example of CU semigroups or Cuntz semigroups. In particular, since it's a Cuntz semigroup of something, it's a CU semigroup. And in here, how does this look like? Well, this is just saying that X must be finite and that it has to be less than 1. Again, one has to prove this, but this is the relation. Okay. Something that I forgot and that's key. In this proof, something that's shown and that's used to then prove that this is a CU semigroup is the following. So at the level of system algebras, this is just the same as saying that A is Cuntz subequivalent to a retract of B for some positive epsilon. So in particular, using this, you can easily prove O2, because A is simply the supremum of this. So you can just think of this whenever you see a pair X way below Y. It's always of this form. Okay, so that's the first example. Second example, which has already appeared, you take the Jason and the Sack algebra, which is a system algebra that you may or may not know. This is 0 infinity. So it's that positive. And this is equipped with the usual order and the usual addition, the one that you might expect. And this identification is not as trivial as this one. So you actually have to work to get this. And so in here, as I said, this is just this. Now, more examples. The easiest non-trivial CU semigroup that you can think of is given by a simple purely infinite system algebra. So if you take any simple purely infinite system algebra, so think of Hilbert algebras, if you will, infinite, then the Cuntz semigroup, by definition, is 0 infinity. So it's 2 points, by definition, if you will, because all the elements have the same Cuntz class, except 0, which has its own. So, and the order here and the addition is trivial, everything. Now, when you look at this, you might say, well, what about this one? Now, this is also a CU semigroup, where the addition is just the usual and 1 plus 1 is infinity. And the order is the linear order, so 0 is less than 1 and 1 is less than infinity. One can prove that this is a CU semigroup, but one can also prove that this is not the Cuntz semigroup of any system algebra. So the range is not full, right? There are CU semigroups that are not attained as Cuntz semigroups of system algebras. It depends on what you know. I'm just going to say the standard answer, and then I can explain more. But if, let's say that you assume that this is the Cuntz semigroup of a system algebra, then the lattice of ideals, which is something that I will introduce in a second, is the same in the Cuntz semigroup and the system algebra. So in particular, the Cuntz semigroup is simple if only if the system algebra is simple. You can show that this is simple, whatever that may mean. And so then it would follow that the system algebra is simple. Okay. So if this isomorphism happened for some system algebras, it had to happen for a simple system algebra. And then such system algebra would need to be weakly purely infinite, which is a notion introduced by Kirchner and Rodan. But for simple system algebras, weak pure infinity is the same as purely infinite. But purely infinite system algebras are 0 infinity, not 0, 1 infinity. So that's the quickest way, but it's like you need to know more things, I guess. But yeah, that's the one-line proof is this one. This would need to be a simple weakly purely infinite system algebra, but this cannot happen because it would then be purely infinite, and this is 0 infinity. Okay, but I will now introduce all these things.
Actually, like 05 or
Yes,
06.
yes.
So does this semigroup satisfy?
It satisfies certainly 05, 06 as well. 07, 08, I'm not sure, but I think it does as well.
Oh,
Yeah. So it's like
all I mean, most semigroup about the city algebra satisfy.
those extra axioms. That's right. Yes. And if I have time during this talk, at the end, I will talk about this. But first, I need to introduce everything that I need for the other talks.
Yeah.
Okay, so last example, which is arguably going to be the most important example during all the talks, is this set. So lower semi-continuous functions from x to n union infinity. And I will now say what this set is. And let's say, for simplicity, let's say x compact and metrizable, compact metric. But you can make it slightly more general. But well, let's say that you have a compact metric space, then you want to look at maps from x to n union infinity such that these inverse images are open. So the usual definition of lower semi-continuity, but instead of going to the real numbers, you're going to n union infinity. I'm sorry, and this is for every n, including infinity. Now, using this definition, you can see that any such map, so f is in here, if only if f is the infinite sum of indicator functions. So if only if this is of this form and this is open. So by this, I simply mean the map that's either 0 or 1. It's 1 in UI and it's 0 everywhere else. And you can prove that any such lower semi-continuous function is the sum of this form. So this set with pointwise order and addition, it's a CU semigroup. Okay. And it's an extremely important one for some of the talks. Not today, but on Tuesday. Okay. So now, what does the compact containment relation look like here? well, because of this, I only need to give you the compact containment relation at the level of indicator functions. And in this case, one has that an indicator function is compactly contained in another, even if U is compactly contained in B. So if you can put a compact in between, that's where the name of the relation comes from. Okay. And also the notation, of course. And well, you may ask, is this the Cuntz semigroup of some sister algebra? And the answer is yes and no. If the dimension is strictly less than 2, then this is the Cuntz semigroup of C of X. But if it's higher than 2, for 2 there is something, but higher than 2, then this is not the Cuntz semigroup of C of X. A way of seeing this is that this is always unperforated and C of X isn't for high dimensions. Okay, so that's one way of seeing this. Okay. Yeah.
Why do you need X to be other than host code? I mean, it's compact and host code. The sister algebra, after all, you define.
Yeah, but is it clear then that this is always a CU semigroup? That's what's.
Oh, I see. You might want to take special lower semi-continuous.
Yes.
Right.
Then yes. Yeah. Exactly.
Okay,
Yeah. Yeah.
That says that particular semigroup
Yeah.
does never arise.
Yes.
Okay.
Okay. So now I've introduced the objects in that category. Now let me very quickly introduce the morphisms, just so that I can state that then the functor preserves inductive limits. So definition. Again, this is same people as before. So one looks at morphisms of positively ordered monoids. Let's call it alpha from S to T, where again, as in the case of sister algebras, S and T will always be CU semigroups for me. So A and B will always be sister algebras, S and T always CU semigroups. So you say that a positively ordered monoid morphism between two CU semigroups is a CU morphism if it preserves the extra structure that we are considering for CU semigroups. So mainly if it preserves the compact containment relation and supreme of increasing sequences. So this is a CU morphism if it preserves a wave-below relation and suprema of increasing sequences. Okay. And so now this is a subcategory of positively ordered monoids. The objects are CU semigroups and the morphisms are CU morphisms.
Do you want to take the zero? Do you want to take the zero into the zero? Is there?
Yes, but I already assume that such morphisms take the 0 to 0. I'm already assuming that positively ordered monoid morphisms take the 0 to 0.
Okay, if there is a zero.
Yeah, but yes, that's the difference between a semigroup and a monoid.
Really?
Yes.
Maybe, okay. Maybe I do that. You think?
So, so then the theorem, and so this is the same paper. And then it was extended by Antoine Pereira until, and the result is that this category has inductive limits, otherwise it wouldn't even make sense to talk about preserving them. So this has inductive limits. And this is now isomorphic. To this. Where again, the point is that this limit is now in CU, not in the category of positively ordered monoids. Okay. And well, the difference, so in here they proved it for sequential ones. So when lambda is countable, and there it's general. Okay, that's the only difference. But the techniques are essentially the same. Okay, so with this, I can give some additional examples, and then I can go to the other things that I need for the other talks. Oh, examples. Well, I call them examples, but one of the implications are theorems, but I will explain all in a second. So if you take a CU semigroup, let's call it S, then this is the Cuntz semigroup of an AF algebra, if and only if it can be written as an inductive limit of this one. Now, as I said, one implication is this theorem together with the examples. And the other implication is that you can lift CU morphisms when they are between finite dimensional sister algebras. And this is not, I mean, so let's say this is this, and it's also that. Okay. So if you are the Cuntz semigroup of an AF algebra, apply this and you get this. And the other way, if you have a CU morphism, then the fact that you can realize it is essentially that you can restrict to the Murray von Neumann semigroup, and then you use the fact that you can lift those up. And that's how you get this. Yeah. Yes.
An arbitrary,
Yes.
an arbitrary, that is an arbitrary index.
Yes. Yeah.
Okay, so that was in the, we only looked at sequences. But,
Yes.
in the second paper, all right, well, I guess I was aware of the second paper extended to arbitrary.
Yeah. Yes, that's the difference. Yeah. Yeah. So
An arbitrary inductive limit just
yes, exactly. Yes. But it's essentially, I mean,
you don't have to have a complication.
no, exactly. Yeah. And then the second example is, if you will, just a generalization of the first. So this is the Cuntz semigroup of an AI algebra. If only if S is the limit on n of copies of this. Okay, so what am I using here? Well, first of all, because the dimension of the space is 1, then this is the Cuntz semigroup of continuous functions in the interval. And so one direction is just given by this. And then for the other direction, you need to show that morphisms between such CU semigroups can be lifted. And that's Super-Elliott. Essentially.
Okay, but who was it the first proof that the Cuntz semigroup of continuous functions identical to what is this?
I usually cite Robert. I usually cite him, but maybe there was someone before him that proved this.
I think that that's special case, I think power may come from.
Okay, then let me write it down as well. So, no, that's completely fine. Okay, so this is in his thesis, but is it published somewhere so that I can cite it? Okay, so it's just the thesis. Okay.
I read the.
So sorry, when is the break? Is it at 50 or?
Well, it would be in the thesis, and I've forgotten the people have to follow that up with the book.
Okay. Oh, the break is in 4 minutes, is that right? Or
No, in, oh yeah, sorry, in 4 minutes.
is it in 4 minutes? Okay,
But I think it's longer.
then I'll take 2 minutes of the break as well. Okay. So then let me very quickly talk about 2 things that will be of importance. One will appear again after the break, and the other one will appear on Tuesday. So the first thing is, this is section 2, so ideals and quotients. So this is the thing that will appear on Tuesday. So I will be very quick at explaining this, and then I will explain it again more calmly on Tuesday. Okay, so definition. Well, let me just put it here. So this is everything that I'm going to explain in this section is Huerca, Robert, and Santiago. So definition, what's an ideal in a CEO semigroup? Well, so one says that a submonoid of a CEO semigroup is an ideal if 2 things happen. So if it is closed under suprema of increasing sequences, and if it's downward hereditary. So what does this mean? Well, essentially that it behaves like a hereditary sister algebra, subsister algebra. So that if you have x less than y and y is in I, then x must also be in I. Okay, that's the meaning of this. And then what you can prove, and again, this is all due to them, is that the lattice of ideals of any sister algebra is isomorphic as a lattice to the lattice of ideals of the Cuntz group. So given any ideal, the Cuntz group of the ideal can be seen as an ideal of CO of A in this sense. And given any ideal here, there is a way of recovering the ideal where it comes from, sister algebras. Okay.
I like the dynamical, make a definition as dynamic as possible. And for instance, for a normal subgroup, I think that's definition because it's the kernel of a group of order.
Mhm.
And then the same with the ring ideal, two-kind ideal.
Mhm.
And then the same with an ideal here.
Yes, but you have to define what the kernel is for stereomorphisms.
It's not just the things that go into the 0L.
No,
Okay, well,
it's
I knew that, I just forgot.
okay. Well, just for yeah. So for everyone else, this is this. So that's formally the kernel of a stereomorphism. Okay. And well, there is also a notion of quotient, which I'm not going to define. I will do it on Tuesday. And let me very, very quickly mention something about functionals, because this will appear now. So This is section 3. Quasi traces. Functionals. Which is actually the original reason why the Cuntz group was defined, in a sense, the relation between quasi traces and dimension functions. But all I'm going to say now, and then in the second talk, I will explain a bit more, is the following. So one says that a map lambda from S to 0 infinity is a functional if it is a positively ordered monoid morphism that preserves supreme of increasing sequences. Okay, so it's a CU morphism that may not preserve the compact containment relation. So that's a functional, and then the set of all functionals is this. Okay, so this is the set. So these are the set of all functionals. Right. Now, all of this just to say what I will need for the second talk, which is theorem. The way that I'm going to state this, this is Elliot Robert Santiago, which is that for a system algebra, this is naturally homeomorphic to a quasi traces on A. If you don't know what this means, just come to me during the break. And for now, just think of it, A being exact, and then this is the set of traces. And homeomorphic because you can equip this and that with a topology that makes them into compact Hausdorff spaces. And how is this given? And that's how I'm going to finish. If you start with a lambda, so a functional, the way that you get the quasi trace, and this appeared, I think, yesterday, is by simply saying this is going to be this. You can prove that this is a quasi trace, and then conversely, if you begin with a quasi trace, then this, and again, there's a lot to prove here, but you can prove that this is the limit on n of tau of A1 over. Okay, so this is just to explicitly write the projection. Okay, and again, I will continue with this after the break. So that's it.